Today we're diving into the world of multiple regression analysis, a powerful statistical technique that helps us understand the relationship between one dependent variable and two or more independent variables. Whether you're working in business, science, or social research, multiple regression can reveal patterns and predict outcomes. In this video, we'll break down the basics, walk through practical examples, and guide you step by step. Let's start by understanding what multiple regression is and why it's so widely used across different fields. Multiple regression is a statistical method that models the relationship between a single dependent variable and two or more independent variables. Unlike simple regression, which looks at just one predictor, multiple regression allows us to analyze how several factors together influence an outcome. This approach is especially useful when real-world situations are complex and influenced by many variables. For example, predicting house prices might depend on location, size, and age of the property. Multiple regression helps us quantify the impact of each factor. Before we move further, let's clarify some key terms. The dependent variable is the main outcome you're trying to predict or explain. Independent variables, sometimes called predictors, are the factors you believe influence the dependent variable. In multiple regression, we use several independent variables to get a more accurate and nuanced understanding of what drives changes in the outcome. Understanding these terms is crucial for interpreting regression results correctly. Heart of multiple regression is its equation. It looks like this: y equals beta 0 plus beta 1x1 plus beta 2x2 plus beta xn plus epsilon. Here y is the dependent variable, x1 to xn are the independent variables, beta 0 is the intercept, beta 1 to beta n are the coefficients for each predictor, and epsilon is the error term. Each coefficient shows how much the dependent variable changes when that independent variable increases by 1 unit, holding others constant. This equation forms the basis for all multiple regression analysis. Multiple regression is widely used because it allows us to account for the influence of several variables at once. This makes our predictions more accurate and our understanding of relationships more realistic. For instance, in marketing, you might want to know how price, advertising, and product quality together affect sales. By including all relevant factors, multiple regression helps avoid misleading conclusions that could arise from looking at just one variable at a time. Like any statistical method, multiple regression relies on certain assumptions. These include linearity, independence of errors, homoscedasticity, equal variance of errors, and normality of error terms. Violating these assumptions can lead to biased or unreliable results. It's important to check these assumptions before interpreting your regression output. We'll discuss each assumption in detail and show you how to test for them in your data. Linearity means that the relationship between each independent variable and the dependent variable is linear. In other words, changes in the predictors are associated with proportional changes in the outcome. If this assumption is violated, the regression model may not fit the data well. Scatter plots and residual plots are useful tools for checking linearity. If you see curved patterns, you may need to transform your variables or consider a different model. Dependence of errors means that the residuals or differences between observed and predicted values are not correlated with each other. If errors are dependent, it can indicate a problem with the model, such as missing variables or time-related effects. This assumption is especially important in time series data. You can check for independence by plotting residuals and using statistical tests like the Durbin-Watson test. Homoscedasticity refers to the assumption that the variance of errors is constant across all levels of the independent variables. If the spread of residuals increases or decreases with the value of a predictor, this is called heteroscedasticity and can affect the validity of your results. You can check for homoscedasticity by plotting residuals against predicted values. If the plot shows a random scatter, the assumption is likely met. Normality assumption means that the errors or residuals of the regression model are normally distributed. This is important for making accurate inferences about the coefficients and for hypothesis testing. You can check normality by creating a histogram or a QQ plot of the residuals. If the residuals follow a straight line in the QQ plot, the normality assumption is likely satisfied. Multicollinearity occurs when two or more independent variables in your regression model are highly correlated with each other. This can make it difficult to determine the individual effect of each predictor and can inflate the standard errors of the coefficients. To detect multicollinearity, you can look at correlation matrices or calculate the variance inflation factor VIF. If multicollinearity is present, you may need to remove or combine variables. For running a multiple regression analysis, it's essential to prepare your data carefully. This includes checking for missing values, outliers, and ensuring that all variables are measured appropriately. Data preparation might also involve transforming variables, creating dummy variables for categorical data, and scaling features. Clean, well-prepared data leads to more reliable and interpretable regression results. Selecting the right independent variables is a critical step in multiple regression. Including too many variables can lead to overfitting, while too few may miss important relationships. Use theory, prior research, and exploratory data analysis to guide your choices. Statistical techniques like stepwise selection can also help identify the most relevant predictors for your model. Once your data is ready and variables are selected, you can run the multiple regression analysis using statistical software like R, Python, SPSS, or Excel. The software will estimate the coefficients for each predictor and provide output that includes measures of fit, significance tests, and diagnostic plots. Understanding how to interpret this output is key to drawing meaningful conclusions from your analysis. Each coefficient in a multiple regression model represents the expected change in the dependent variable for a one-unit increase in that predictor, holding all other variables constant. Positive coefficients indicate a direct relationship, while negative coefficients indicate an inverse relationship. It's important to consider the context and units of your variables when interpreting these values. Statistical significance tells us whether the relationship between an independent variable and the dependent variable is likely to be genuine or just due to random chance. This is usually assessed using p-values. A small p-value, typically less than 0.05, suggests that the predictor has a significant effect on the outcome. However, statistical significance does not always mean practical importance, so always consider the real-world context. R-squared is a measure of how well your regression model explains the variation in the dependent variable. It ranges from 0 to 1, with higher values indicating a better fit. However, adding more variables will always increase R-squared, so it's important to also look at adjusted R-squared, which accounts for the number of predictors. Good model fit means your model captures the main patterns in the data without overfitting. Analyzing the residuals, or the differences between observed and predicted values, helps you assess the quality of your regression model. Residual plots can reveal patterns that indicate violations of assumptions such as nonlinearity or heteroscedasticity. Ideally, residuals should be randomly scattered around 0, showing that the model fits the data well. Always check residuals as part of your regression analysis. Outliers are data points that deviate significantly from the overall pattern. Influential points are those that have a large impact on the regression results. Both can distort your model and lead to misleading conclusions. Use diagnostic tools like Cook's distance or leverage plots to identify and assess these points. Deciding how to handle them depends on whether they represent errors or genuine variation. In dealing with categorical independent variables, you'll need to create dummy variables. These are binary variables that indicate the presence or absence of a category. For example, if you have a variable for gender, you might create a dummy variable that is 1 for female and 0 for male. Dummy variables allow you to include qualitative information in your regression model. Sometimes the effect of one independent variable depends on the level of another. This is called an interaction effect. You can include interaction terms in your regression model by multiplying the variables together. Interaction effects help you capture more complex relationships in your data and can provide deeper insights into how variables work together to influence the outcome. Using the best set of predictors for your regression model can be challenging. Model selection techniques like forward selection, backward elimination, and stepwise selection help automate this process. These methods add or remove variables based on statistical criteria, aiming to find a model that balances complexity and predictive power. Always validate your final model using new data or cross-validation. Overfitting occurs when your model is too complex and captures noise instead of the underlying pattern. Underfitting happens when the model is too simple and misses important relationships. Both situations reduce the usefulness of your model. Use techniques like cross-validation and compare model performance on training and test data to avoid these pitfalls. Cross-validation is a technique for assessing how well your regression model generalizes to new data. The most common method is k-fold cross-validation, where the data is split into k parts and the model is trained and tested k times. This helps you estimate the model's predictive performance and reduces the risk of overfitting. Always use cross-validation when building predictive models. Let's look at a practical example. Suppose you want to predict house prices based on factors like square footage, number of bedrooms, and location. By running a multiple regression analysis, you can estimate how much each factor contributes to the price. This approach helps buyers, sellers, and real estate professionals make more informed decisions based on data rather than guesswork. After running the regression, you'll get an output table with coefficients, standard errors, t-values, and p-values for each variable. Focus on the size and sign of the coefficients, the significance levels, and the overall model fit statistics like R-squared. This information tells you which variables matter most and how well your model explains the outcome. While multiple regression is a powerful tool, it has limitations. It assumes linear relationships and can be sensitive to outliers and multicollinearity. It also doesn't prove causation, just association. Always interpret results carefully and consider alternative models or additional analyses if your data or research question requires it. If your dependent variable is categorical, such as yes-no or success-failure, logistic regression is a better choice than multiple regression. Logistic regression models the probability of an outcome and is widely used in fields like medicine and marketing. It's an important extension to understand when working with different types of data. When relationships between variables are not linear, polynomial regression can be used. This involves adding squared or higher-order terms of the predictors to the model. Polynomial regression allows you to capture curved relationships and can improve model fit when linearity is not appropriate. Ridge and lasso regression are techniques that add penalties to the regression coefficients to prevent overfitting, especially when you have many predictors. Ridge regression shrinks coefficients toward 0, while lasso can set some coefficients exactly to 0, effectively selecting variables. These methods are valuable when dealing with high-dimensional data. In reporting, the results of a multiple regression analysis include the regression equation, coefficients, significance levels, R-squared, and any diagnostics you performed. Use clear tables and graphs to help your audience understand the findings. Transparency and clarity are key to effective communication of your results. Some common mistakes in multiple regression include ignoring assumptions, overfitting the model, misinterpreting coefficients, and failing to check for multicollinearity. Avoid these pitfalls by following best practices, checking diagnostics, and always considering the context of your data and research question. To get the most out of multiple regression, always start with a clear research question, prepare your data thoroughly, check assumptions, and interpret results in context. Use visualizations to explore your data and communicate findings. And remember, no model is perfect. Use regression as one tool among many in your analytical toolkit. There are many software options for running multiple regression, including R, Python, SPSS, SAS, and Excel. Each has its strengths and user community. Choose the one that fits your needs and skill level. Most provide built-in functions for regression analysis and helpful diagnostic tools. Model diagnostics help you assess whether your regression model meets the necessary assumptions and performs well. Look at plots of residuals, leverage, and influence, as well as statistics like VIF and Cook's distance. These diagnostics guide you in refining your model and ensuring reliable results. In using multiple regression, consider ethical issues such as data privacy, informed consent, and potential biases in your data or model. Responsible analysis means being transparent about limitations and ensuring your findings are used appropriately. Ethics should always be part of your analytical process. Effective communication of regression results involves translating statistical findings into clear, actionable insights for your audience. Use visuals, summaries, and plain language to explain what the results mean and how they can be applied. Tailor your communication to the needs and background of your audience. Multiple regression is used in countless real-world scenarios, from predicting sales and customer behavior in business, to analyzing risk factors in healthcare, to studying social trends in research. Its flexibility and power make it a go-to tool for data-driven decision-making across industries. Imagine a company wants to understand what drives the success of its marketing campaigns. By using multiple regression, they can analyze the impact of budget, channel, timing, and creative content on sales outcomes. This helps allocate resources more effectively and improve future campaigns based on data-driven insights. In healthcare, multiple regression can be used to study how factors like age, lifestyle, and treatment type affect patient outcomes. By analyzing these relationships, healthcare providers can identify key risk factors and tailor interventions to improve patient health. This approach supports evidence-based medicine and better patient care. Education researchers often use multiple regression to explore how variables like class size, teacher experience, and school funding impact student achievement. This helps policymakers and educators make informed decisions about resource allocation and teaching strategies to support student success. Let's recap the key points. Multiple regression allows you to analyze the impact of several variables on an outcome, check assumptions, interpret coefficients, and apply the results to real-world problems. Remember to prepare your data, check diagnostics, and communicate findings clearly. Multiple regression is a versatile tool for data analysis. If you want to learn more about multiple regression, there are many excellent books, online courses, and tutorials available. Explore resources specific to your field and practice by analyzing real datasets. The more you apply these techniques, the more confident you'll become in using regression for your own projects. Multiple regression analysis is a foundational skill for anyone working with data. By understanding its principles, assumptions, and applications, you can unlock valuable insights and make better decisions. Keep exploring, keep questioning, and use regression as a powerful tool in your analytical journey. Thank you for joining us on this exploration of multiple regression analysis. We hope you now feel more confident in understanding and applying this essential statistical technique. Remember, the key to mastering regression is practice and continuous learning. Good luck with your data analysis projects.